Okay. Hi, everyone. So I'm Jörn-Henrik Jacobsen. I work at the Vector Institute in the University of Toronto as a postdoc. And I'm going to talk about unsupervised learning with autoencoders and likelihood-based generative models. So first, a disclaimer, this is not exhaustive. I won't talk about GANs. I won't talk about self-supervised learning because it would have been too much for that hour, in my opinion. So great. So take like you should know that. Okay, before I motivate unsupervised learning, I want to do a recap on supervised learning. So supervised learning is essentially deep learning's biggest success story. In supervised learning, we want to learn some function f parameterized by theta, usually a neural network, that maps inputs to known targets. So we have a data set of input and target pairs. Inputs here are our axis, and our targets are our y's. And then we have a training objective, which is essentially the maximum likelihood objective, typically. So we want to minimize the negative log likelihood of the targets given our inputs and the current parameter set. Maximum likelihood is the dominant paradigm for supervised learning. And yeah, basically, that's what is done. So one example is image classification. So you have a bunch of images that have been labeled by someone beforehand. And now you basically want to learn this function that maps all the flower images to the label flower, all the elephant images to the label elephant, and so on and so on. So you train your model on the training data set, and then you hope it generalizes to the test set. Another example is semantic segmentation. So here, that's basically a classification of the single pixels. So you want to essentially have a network that gives you a semantic grouping of the pixels. Here, one semantic group would be the background pixels. Another group is the pixels that are actually the cyclists. Another group would be the bicycles themselves. Another example is image captioning. So given an image, you actually want to map it to a sentence. For instance, here, that image ought to be mapped to a sentence called, which is construction worker in orange safety vest is working on road. And there are many more examples of supervised learning, so I'm going to stop now and go into basically a more like general characterization of it. So what you often have in supervised learning is that you have very high dimensional inputs. If you have ImageNet classification, for instance, your inputs have around 150,000 dimensions. And you will want to map those to a very low dimensional target vector, basically. So in ImageNet, it's like in ILS VRC challenge, it's 1,000 dimensional target vector, which is binary. So your inputs are high dimensional and the targets are low dimensional. And that means that basically lots of variability has to be discarded throughout the layers of your network to master the task. And maximum likelihood training allows you to learn what to discard from your input target pairs. Right, so there are some issues with supervised learning. So first of all, supervised learning only requires a narrow understanding of the input distribution of your data set, basically, just enough to extract labels reliably from your train set. So this narrow understanding can lead to poor generalization if data sets and tasks are not large and diverse enough. And also, labels can be expensive. So many examples exist where it's difficult to obtain high-quality input target pairs. For instance, if you need to label label pathologies in medical images, you need a specialist that does that. It's very expensive and very cumbersome. So the promise of unsupervised learning is basically that we want to make use of the fact that unlabeled data are abundant. And the core idea of unsupervised learning in a nutshell is that we want to learn as much knowledge from the unlabeled data as possible. And then once we have actually trained a model that basically knows a lot about our data, this resulting model has gained a holistic understanding of the training data. And we can use that model basically to adapt to downstream tasks or sort of get summary statistics of our data and so on from that. So that sounds great, but how do we extract this knowledge from unlabeled data? That's essentially one of the major questions here. Right, so here are some examples of different data modalities. We have an image, we have some text, we have raw audio. So the inputs are, again, very high dimensional. There's lots of structure, and it's unclear what variability, what structure to pay attention to, right? So we can't just, in this case, we can't just discard variability because we don't really know what we will need later on downstream. So we need a general objective which formalizes summarizing the data, essentially. So we want to summarize whatever structure there is in the data, and we want to discard as little as possible about it. Right, so here you see basically how data can look like to a computer. It's really just like strings of numbers, and here we start again with the data set without targets. So now we only have the axis and no y. So one option is actually to learn a compressed representation of that data. So one way to formalize compression is that we want to project the data to a lower dimensional manifold and represent it by location on this manifold, essentially. So that's the core idea of principal component analysis, which is actually an unsupervised learning algorithm in that sense. So here's an example. We have some original data space, three-dimensional in this case, of some gene data, and PCA represents a d-dimensional data in a linear n-dimensional subspace. So we want to find a plane which has dimensions smaller than our input data, and we want to project data points onto this subspace spanned by orthogonal components in directions where the data has the highest variance. So we lose information about location in the remaining orthogonal directions, but this is not a problem because those dimensions had low variance to begin with, so we didn't lose much information. So you see, after PCA, we project it down to a two-dimensional space, and then we have a summary statistic of the data. So linear autoencoders are actually very similar to PCA. So if you train them with mean squared error, so basically you want to have, you have an input, for instance, an image X, that gets mapped to a low-dimensional representation Z by some linear transformation W1. And from Z, you actually reconstruct X, so that's your X tilde. And then you measure the mean squared reconstruction error between your input and your reconstruction. So if you train this with mean squared error via backpropagation, then actually if the bottleneck is lower dimensional than the data, the result is actually equivalent to PCA. However, the bottleneck units will most likely not correspond to the principal components or basically the directions, because they do span the same space, but maybe rotated or skewed. However, the advantage here is that we can generalize this to the nonlinear case. So instead of basically having W1 and W2, we could have nonlinear neural networks and do a nonlinear version of this autoencoder. Again, the same loss function, mean squared reconstruction error, but now we have a nonlinear generalization of PCA, which can learn to project data onto nonlinear manifolds. So that's a powerful tool of data compression, for data compression. So what we can do, let's say we've trained this on a lot of unlabeled data. So then we can freeze the encoder, throw away the decoder, and use the Z representation basically to train some like downstream head on that. So basically we train the classifier also with little data and fine tune only with like a couple of labeled examples. So that can work very well in some cases, but there are also problems with this. So the compressed Z representation potentially has a very complex structure. So thus, using this representation in downstream tasks can be hard, because it could be hard for, say, a linear classifier as the downstream had to sort of disentangle the things you care about. And also generating new data from your autoencoder in a principal way is hard, because if you have, if you put in one X, that gives you another Z basically, and then you wait from that, and you have another Z and from another X, you don't really know what's the path between these two inputs. So you could generate new X tilde, basically. Right, so an alternative is to maximize the likelihood of the data. So the maximum likelihood objective, as we've seen before for supervised learning, but this time without labels. So we basically have, again, sum over the whole data set of the negative log likelihood of the probability of the data, or of the likelihood of the data under our model, parameterized by theta. So this is equivalent to minimizing the chiral divergence between model and data distribution. And any divergence is zero if and only if the two distributions are the same. So basically, minimizing the negative log likelihood of of the data under our model corresponds to basically fitting a model to the data that at some point, once you converge completely, has the same distribution as the data. So the implication of this is that we incentivize the model to learn everything about the data. Right, so and that brings us to variation autoencoders. So we can reinterpret the nonlinear autoencoder as a latent variable model. So we basically say, instead of log p of x, we introduce a latent variable z. So then log p of x equals the log of the integral over z, p of z times p of x given z. Then we actually say, okay, we do a variation approximation to the probabilistic encoder, which we call q parameterized by theta, z given x. Then we apply Jensen's inequality, essentially just swap the expectation in the log. That gives us a lower bound. And then we actually have the variation autoencoder objective, which has two terms. This inequality, basically the lower bound is tied when the variation approximation matches the true posterior. So the final objective is also often called the elbow, which is the evidence lower bound, because it lower bounds the true data log likelihood. So it's a reconstruction term and a regularization term. So the reconstruction term essentially takes care of that we can decode from Z properly, so we can reconstruct images correctly, and the regularization term actually regularizes our latent code Z to have a certain structure. So that's a lower bound on the data likelihood, which we can maximize during training. The concept is very general, and you can have many choices of encoder, decoder, and priors, basically. So some applications here. So once you have trained your variation autoencoder, say on celebrity faces, that's something what people really like to do for some reason, we can generate new data. For instance, by interpolating in latent space. So here, this is trained on celebrity faces, and basically just you take the corner images and linearly interpolate in the latent space, in the space of Z, and just generate the corresponding images along these lines. And then that's basically what you get here. The VAES have been pushed to basically produce very, very impressive samples recently. Here we see samples from a VQ-VAE2, which is basically an extension of the VAE, which adds a discrete encoder and a learned prior into the mix. And those not only do these models produce compelling samples, but they also have been shown to actually learn interesting latent representations. Another application of variation autoencoders is actually what is the state of the art in adversarially robust classification on MNIST. So the idea is really to use variation autoencoders as class conditional generative models and then get a robust classifier from this. Also, there have been promising results on fair representation learning with variation autoencoders. So one major goal of fair representation learning is that you want to learn a representation which is invariant to changes of some sensitive attributes in your inputs. And you can easily phrase this as constraints on your latent space, basically on your prior when you train your VAE. Right. So then there are also other alternatives which don't require you to actually compute a lower bound, but actually can give you exact likelihoods. So if we use what is called the chain rule of probability, we can actually break the high-dimensional modeling problem of modeling all of P of X into one-dimensional conditional density modeling problems. So for instance here, for say a time series or like something like audio, so we can say, okay, P of X equals P of X1, X2, and so on until Xn, where n is the number of dimensions essentially that we have. This equals the product of all the conditional probabilities. So this can be easily extended to higher dimensional data like images or video, and also is easy to extend to other domains and so on. So these models are typically called autoregressive models, and now we actually have a way of actually doing exact maximum likelihood instead of having to compute the lower bound like in the VAE. So here's an example. For instance, if you want to model a sentence, so this sentence happens to be bigger models are always better. So you first have the probability of bigger, then you have the probability of models given bigger, then you have the probability of R given bigger models, and so on. So that's basically how you model the whole sentence. And the negative log likelihood objective is essentially, again, the sum over your data set, and then the sum over the negative log likelihood of the conditional probabilities. So in practice, the probability is a discrete softmax output, and that ends up being very similar to actually training a classifier. You really just train a classifier to predict the next token in your data. And the conditioning is usually done via a network state. So for instance, with an RNN or an LSTM, masked convolutions, or transformer modules. So there's basically many choices for this, and usually you choose something that is natural for your data. Right. So there's one caveat, and that is that actually the ordering of this factorization is very important. So if you, on the top left, you see a naive way to basically do the ordering if it would be an image that you want to model. So you would just really just go pixel by pixel, row by row. But it turns out that actually if you do more clever orderings, which basically are, for instance, multi-scale or sort of take the structure and the channels into account, you can boost the performance a lot, and this is very important. And the recent progress is mostly based on finding better orderings for the data in these models. Right, here you can see the pixel RNN, which was one of the first major breakthroughs in this autoregressive modeling of high-dimensional data. So there are some samples from ImageNet, 64 times 64. Then the SPN, which was presented at iClear, at last iClear, some samples from ImageNet 128 times 128, which look much better already, but this is mainly due to actually better ordering of the factorization, essentially. And also some improvements in the models, but these are less significant. Wavenet is also another of these autoregressive models, so it's a model that can actually model high-dimensional raw audio. So Wavenet uses dilated causal convolutions to model audio autoregressively. These dilated convolutions have a large receptive field because that's important due to a high temporal resolution of raw audio, and it works extremely well. It's actually, I think, in the Google Assistant or something these days, right? And these autoregressive models have been applied to many more modalities like language, tabular data, and so on. And in many, they are actually also the state of the art. So to summarize, autoregressive models enable tractable and expressive modeling of arbitrary data distributions via the chain rule of probability. We don't have any mode collapse or something, and we can, and generalization is easy to quantify. So basically just measure the likelihoods on the test set and see if we have a big gap between train and test. And they are the state of the art for density estimation in various domains. Downsides are that the ordering of factorization matters a lot. So that's something you have to really think about. You need domain knowledge for that. The training can be parallelized, but the sampling is very slow because you really have to generate the data one by one usually. And these architectures that people use to do autoregressive modeling on state-of-the-art levels are very different from the state-of-the-art discriminative models that people use for classification and so on and so on. So this is potentially upper bounding the performance on downstream tasks. So if you want to basically pre-train your model unsupervised with lots of unlabeled data, and then you want to fine-tune it with some labels on your, for some task, then you can only become as good as you would be with like only training with labeled data, basically. And those models are basically not that good if you just train them as supervised models. Okay. Any questions so far? Yeah.
In the case of audio processing, it is well known that bidirectional, leveraging bidirectional LSTM modeling using bidirectional approach has a lot of advantage. The way of factorizing with respect for the autoregressive one is unidirectional. So what happens for XFT, it is on all the ones, next one, next two, and so on. So given that there is information that can be generated out of what happens in a non-causal fashion, can we incorporate that into the autoregressive model?
Yeah, you would have to think about like how if you can come up with a certain with a particular factorization that takes it into account. Then you could, but I'm not sure. Yeah. Yeah. No, so the idea is really that you phrase every modeling problem as a sequential problem, more or less. So you can just by the chain rule of probability, you can just rephrase any joint density as conditionals, essentially. So that's just a general principle, right? Yep.
One of those autoregressive models doesn't suffer from mode collapse.
Right, because of the nature of the KL divergence. So it basically the objective basically makes you you have to put assign density to every point where you actually see data. So if you don't do that, you get penalized heavily. Whereas a GAN, for instance, doesn't get penalized if it doesn't model a certain data point, for instance. So it's really due to the nature of the KL divergence in the forward direction, right? Yeah.
So can you say that VAES learn better representations than the normal autoencoder?
Better is, it really depends on what you want. So for sure, if you want to incorporate structure into your latent representation, then VAE is the way to go because it gives you a principled way to do so. And also you can, for instance, you get bounds on the likelihood, so you can actually have a principled way to measure outliers or look for outliers and so on. So it's not per se better, but it gives you a new tool to structure your hidden representation, essentially. Yeah. Right. Yeah.
Can you provide any insight about the dimensionality of the data space in a way to make sure that the relevant features are being preserved?
Well, essentially the dimensionality of the data space in the autoregressive model is the same as the input data space because you really have to model everything as conditional densities. In VAES, it's unclear. So it depends. If the data is compressible by a lot, then basically you can have a very small bottleneck and it would still work well, but there's no principled way of determining that really. Yeah. Yeah. Yeah.
Can you use a different metric apart from the KL divergence to measure the divergence between the prime and the posterior? And if so, like, what are the advantages and disadvantages?
Right. So KL divergence in the forward direction usually gives you a what is called mode covering behavior. So you basically have to assign probability mass to wherever you see data. You can also use the reverse KL divergence, but the problem is for that you need to evaluate actually your true P of X, and you don't have access to that. So GANs are basically thought to do something like that implicitly, but you can. There's not really a nice way to train reverse KL divergence, for instance, in a general form. Yeah. So that's also a bit of a problem because now you actually have these models that assign a lot of high densities to areas where you have actually never seen data, just in case, you know. Yeah. Yep.
So for autoregressive modeling of sequential data, I've seen a problem where when you sample from these models, your samples tend to collapse onto the mean of the data distribution. So
Uh-huh.
what is this for this?
No, sorry, I'm not sure. Okay, so then, so as I said, basically, autoregressive models have very different structure than the state-of-the-art indiscriminate tasks, which are, for instance, ResNet-like architectures. So why does this matter? So if the model does not work well in a discriminative setting, then it probably won't provide much gain when pre-trained unsupervised, right? Because the best you could do would be to train with all the data you have, with all the labels that are associated with it. So if that model is already bad, then you wouldn't have to hope for it being better if you train it with a lot of unsupervised data and then in an unsupervised way on a lot of data and then use a little bit of data to fine-tune it. However, there's a family of generative models which is quite similar to the best supervised models, which is actually normalizing flows. So they provide a simple and elegant way to train with exact maximum likelihood, again, also via the change of variable formula. So the change of variable formula has the following form. The log P of X equals the log P of Z, where Z is basically your transformed X, so your f of X essentially, plus the log absolute determinant of the Jacobian of your function f that transformed X into X into Z at the point X. So I want to give you a little intuition about this. So we have some P of X that is transformed by some bijective function f of X, and this results in some probability density distribution P of Y, which we don't really have access to. We don't know the functional form of that. So here you see on the x-axis is mirrored, it's an exponential distribution, e to the power of minus x. We map this through square root of x, and then we get a new density essentially. So under this transformation, the intervals are stretched. However, we do know that the probability of y landing is somewhere in the range b prime, which is essentially between y and y plus dy on the y-axis, is equal to the probability of x landing in the area basically of in b, which is x plus x to x plus dx, because these are essentially equivalent events, and we really just transform them. So, and then the change of variable formula relates these two areas under the graph to one another essentially. So by considering the differential volume element, we can see that P of y times dy equals P of x dx, which is really just what I just said. And then we can rewrite that as Py equals P of x times the modulus of d of x divided by dy. So this actually gives us a way of, without actually knowledge of the functional form of P of y, to evaluate the density of P of y. So that's the main idea actually of normalizing flows. You basically have implicit access to your P of y distribution and can, even though you only know P of x in this case. So if we generalize this to higher dimensions and take the log, we end up with the objective I said. So it's the log P of x equals the log P of y plus the log determinant, the log absolute determinant of f at x. And that's actually the training objective on normalizing flows. Right. So now we know how to relate densities transformed by invertible functions to one another. And the normalizing flow idea is to specify a simple base distribution in output space. So in this case, in our Z space, so we know this density. For instance, it could be factorial Gaussian, which is something that people use a lot. We can evaluate the density of this, and then we compute the complex data likelihood in input space via the change of variable formula. So we don't know the functional form of P of x, but through the change of variable formula, we can still evaluate it. So now we have some problems. First of all, we need an expressive bijective deep network for this that actually maps from x to z and back. We need the log determinant of the Jacobian of this network to be easy to compute, because we need it to correct the density, essentially. And then, if we want to sample from the model, we also require to have a tractable inverse. So here you can see again the inference is we essentially morph the data space X through, which like this arrow is our invertible network, essentially, to some latent space Z. In this latent space, we have trained, actually, we have trained this latent space to follow a certain structure which is given by our prior. In this case, it's Gaussian. And then we can evaluate the density there, and that's how we train. And at generation time, we sample from a Gaussian, invert the network, and then we get the complex samples from the complex density back. One approach to do this, so most progress in normalizing flows is really about building expressive bijective networks with tractable Jacobian determinants. One approach to this is nonlinear independent component analysis, also called NICE. And NICE builds invertible networks as composition of volume-conserving invertible blocks. So recall the ResNet block. So ResNet block is really just x2, which is basically the output of the first layer, equals x1 plus f of x1, right? I guess everyone is familiar with that. So the so-called coupling block, that's basically how the reversible ResNet blocks are called in NICE, differs in a dimension splitting scheme. So instead of feeding x1, so instead of having x1 plus f of x1, we now split x1 into two parts, basically. It could be, for instance, splitting it along the channels. So we say the first half, the first half of the channels is our x1 tilde, and the second half of the channels is our x1. So and then we process these two halves independently, but basically condition the transformation on them. So x2 is then x1 tilde, and x2 tilde is x1 plus f of x1 tilde. So you can see the schematic of this on the top right. That's basically how it looks like. It's really just like a ResNet block, but you first split your input into two halves. And after every block, you switch essentially the ordering of the two. So and what this gives you, so that's basically, you see here on the bottom right how the Jacobian of this looks like. So then the Jacobian is triangular. So that basically means that it's very easy to compute the log determinant of this Jacobian, which is really just the sum of the diagonal entries here. The inverse is also simple and efficient. You can see that we really just replace the plus with a minus. So we can get back x1 tilde by simply just, it's just x2. And then we input x1 tilde into our f of x1, into our f, and subtract that from x2 tilde. And then we get x1 back. So as I said, the Jacobian is triangular with ones on diagonal. So NICE is what is called volume conserving. That means that the log absolute determinant of the Jacobian is 0. So we don't have to correct for a change in density here. Is that concept clear, or does anyone have any questions about it? Okay. To whom is it clear? Okay, so the idea is really just that we want to build something that is easy to invert, and this dimension splitting gives us a tool to do that, right? Okay, so now I'm thinking if I should maybe go. So just ask some questions to see which part wasn't clear. Yep.
So we have a function that has a Jacobian determinant that is 1.
Yes.
Everywhere, but it's not a linear function. And
Yeah.
It's potentially not linear. It's like how
Yeah, so that's really just due to the construction of this. If you have an upper triangular mapping with ones on the diagonal, which actually this dimension splitting and basically independent computation, like you see here, that's basically what it gives you. So these blocks will always have a Jacobian structure like this. The lower or upper triangular, but always ones on the diagonal. Because you have really no multiplicative interactions there, so nothing is scaled. You really just add one half to the other and so on. Yep.
How do you split x into x1 and x1 tilde?
Sorry?
How do you split x?
That's arbitrary. It just has to be mutually exclusive, so to say. So x1 and x1 tilde need to basically, so together they have to be the whole of x, and x1 cannot contain any dimensions of x that are also contained in x1 tilde. So for instance, split in the middle of your channels, or split your image in half, top and bottom. Basically everything is valid. You could do a splitting which is maybe a checkerboard pattern or something like that. And actually, it's a good question, because this is like a lot of progress in normalizing flows is based on trying to come up with good splitting that is like appropriate for the data domain.
So is that why you can't just make a triangular matrix with ones on the diagonal, because you have like interlacing?
Well, that's just one way of parameterizing such a matrix.
But like in this instance, you have zeros and there's like two triangles with like.
Right. Yeah, you could just parameterize your transformation exactly this way. I mean, that's one way to parameterize it this way, right? So in a way, that's what we're doing. We're picking, yes, and make it learnable in an efficient way. So, yeah. Yeah. I mean, up to numerical instability, so yes. Right. So you can only approximate them by sort of, yeah, here, but here you have basically you're completely right. So to approximate very, very skewed things, you actually need to change the volume and scale dimensions, which is actually exactly what sort of the next iteration of this work did, which is the next slide. Yeah.
How is this related to independent component analysis?
Right. So what we do here is basically we try to map the data into a space where we basically have independent components. So depending on the prior we choose now on our Z space, on the output of this network, we have a particular structure in the final hidden representation. So and if we choose that prior to be factorial, so basically we want to have no interaction between the dimensions, then we actually get independent components if we manage to minimize this perfectly. So that's really essentially the old school independent component analysis is really like this here. At least some ways of doing it is really having a linear transformation where you compute the log determinant of the Jacobian efficiently, or maybe it's also 0, sorry, and then you try to map it to some prior that has a factorial structure. So then you remove all the dependencies in your latent representation. So if you look here, in the latent space Z, you see basically this is completely spherical, and then there's essentially, so you have a diagonal Gaussian structure here. Mm-hmm.
When we are projecting, let's say college projecting x1 to x2, if x1s have much higher dimension compared to x2, for example, even just two labels, then some part of this information is going to be lost.
Well, so F needs to, the output of F needs to have the same dimensionality as x1 here. So let's say x1 tilde has 2 dimensions and x1 has 100 dimensions, then actually your F, your nonlinear residual block, basically needs to have 2 inputs and 100 outputs, so you can add them together here. Does that make sense?
Yeah, right. But then, so some part of the x2 captures the information, and the rest is just a random Wavenet variable, right? Usually. And when you invert it, you put the label information, and then you sample from a random distribution, but you don't know, for example, about the details of this random variable.
Well, so as I said before, once you have minimized the KL divergence, then actually the distribution described by this model is the data distribution. So if you sample from your prior, transform back, you get samples from that are actually from the data distribution. Yeah. Okay. Anything? Did I miss someone? Yep.
So does this mean that the input dimensionality and the output dimensionality in the end have to be the same?
Yes, exactly.
So there's no compression going on?
Well, lossless compression. So there's a notion of lossless compression where you still summarize the data sort of in a different way, but yeah, so the dimensionality is the same. So, excuse me? Yeah. So right. So all the information about the input is actually is preserved throughout all the layers.
I have a quick question on how do you show that there is a volume preserving invertible block? So you basically have a composition of volume preserving blocks, right?
Yeah.
And how do you show that each of these is volume preserving?
Right. If you have a composition of volume preserving blocks, it's really just the product of the log determinants. So then of the determinants of the Jacobian. So then you have a volume conserving function. Yeah. Okay. So as already noted, the first obvious extension is how to make this non-volume conserving. So that's what the so-called real MVP did, which is a direct follow-up of this work. So here we actually introduce, instead of just having these additive interactions, we now introduce multiplicative interactions, which is essentially dimension-wise multiplicative interactions. And now you can see that the lower diagonal actually has different values that are not just one. So now actually the volume of the volume can be changed and the density can be stretched in different ways. So now the log determinant of this Jacobian is not 0 anymore, but we can efficiently compute it by just summing over the log of these diagonal entries. So then, yeah, so basically just like NICE, these models are trained by minimizing the negative data log likelihood, which is given by the change of variable formula. So we basically, again, the sum over our data set minus the log of P of Z of f of x, so in our output space, minus the log of the absolute determinant of f at x. Right, so then there was GLOW, which is again an improvement upon real MVP. So there was NICE in 2014, real MVP in 2016, and then GLOW in 2018. GLOW improves upon real MVP in multiple ways. So one thing is that now we actually they learn the dimension splitting with a 1x1 convolution before a generic splitting along the channels. So as you said, turns out that this is pretty important, and now they really just interleave a 1x1 convolution with all with these simple coupling blocks with a simple like channel splitting, and that helps a lot. They remove the batch dependency, which was due to batch norm in the original real MVP, which helped to converge fast, but at the same time also gives you a lot of instability. And then they simply just scale the models up by a lot. So now the coupling block is on the right, and then on the left and on the right we see the full network. So we basically just stack multiple coupling blocks on top of one another, and in between we have what is called a splitting operation. So say after a third of the network we factor out half of the variables already and model them right away. So then after another third of the network we factor out half of the variables, model them right away, and so on. So that gives us because what they do here is also what is called a squeeze. So it's in TensorFlow, for instance, it's called, I think, or PyTorch is called a pixel shuffle. So you really do what could be seen as an invertible downsampling. You shuffle pixels from space into channel dimensions, and that gives you sort of a multi-scale view on your data. So then at the multiple scales, you factor out half of the dimensions to model low-level details, mid-level details, and sort of high-level details. Right, and then with GLOW, the results of these flow models actually started to close the gap to autoregressive models. And also what this showed is that actually stability, as well as the hand-designed dimension splitting are major bottlenecks in flow models, and they resolve some of that and already improved performance by a lot. Right, here we can see again some improvement. So NICE, the samples are basically, so these are CIFAR 10 samples. The NICE samples are from 2014. The negative log likelihood is 4.48. Real MVP is already much nicer samples, much better likelihood. And then GLOW improves upon that even further. Right, so that's essentially, now GLOW is one of the most widely used flow models. And you can see they scaled this up to huge images, so they generated, again, celebrity faces in high quality by training these models on a lot of GPUs. And what you can also do is you can encode images. So on the top left and on the bottom right is actually the two researchers that wrote the GLOW paper, and they can encode their own faces into the model. Even though they have never been seen in the training set, the model generalizes to those data points, and you can sort of interpolate in semantic dimensions that you get from the attributes in the CELOP A data set. So then you can sort of manipulate, make the faces older, younger, and whatnot, and interpolate between the two personalities. Right. So then another question is, can we take it even further? And then there was a paper called Invertible Residual Network, which asked the question if we can guarantee invertibility in state-of-the-art non-invertible networks. So that means basically without any dimension splitting. Can we get all these properties? So because the dimension splitting has been shown to be very important, and so it would be nice to get rid of it altogether. So there's a remarkable similarity between ResNets and Euler's method for ODE initial value problems. So if you see, again, the ResNet update, so the xt+1, which is basically the output of our ResNet at the tth layer, so to say, equals xt plus g of xt, right? So that's familiar. And the Euler update is actually almost the same. It's xt+1 equals xt plus h of f of xt, which is essentially just a scaled version of that. And that's a method to actually to solve ODE initial value problems. And there's also an associated dynamics backward in time, which is given by the implicit backward Euler discretization. So now if you want to go back from the output of the of the tth layer to the, sorry, of the t+1th layer to the tth layer's input, then we get these equations on the bottom. So xt equals xt+1 minus g of xt. So now we have a problem. Xt is on both sides of the equation. So basically, so now we need a method for solving that. And such problems can be solved with a fixed point iteration scheme. So the inverse is basically initialized with the output of the block, so here called y. And then we just iterate over y minus g of xi, and I index is basically the current iterate. So that's how we can invert a standard ResNet block. And the sufficient condition for this, for invertibility of this ResNet block, is actually a contraction. So the Lipschitz constant of g needs to be smaller than 1. And then if that's the case, this guarantees the convergence of the iteration due to the Banach fixed point theorem. So basically, if the Lipschitz constant of our residual block is smaller than 1, then we can invert it with this fixed point iteration scheme. So now we don't need any particular structure anymore. We just have to make sure somehow that the Lipschitz constant of our residual block is always smaller than 1. And now, the question is, how do we do that? And we do that actually by applying a spectral normalization to all the weights in our residual blocks. So we basically spectrally normalize all the linear operators and scale them with a small factor such that the largest singular value is just below 1. And then we basically have this property satisfied. Right, so then here you can see some inversions of residual networks. So on the top, you see original digits. We pass them through the whole ResNet. And then with the fixed point iteration scheme, we compute the inverse of the network. And on CIFAR 10, we do the same, basically. So then you see if it's unconstrained, so if we don't constrain the Lipschitz constant of the network, then on MNIST, we can even already recover the inputs that way. And if we constrain the Lipschitz constant to be smaller than 1, then still works well. On CIFAR 10, it looks slightly different. If we use the fixed point iteration to actually compute the inverse, it doesn't work without the constraint. If we put the Lipschitz constraint on the blocks, then we can recover the input. And interestingly, the performance is not significantly affected in all cases when you actually look into the classification accuracy of the invertible and the non-invertible ResNet. Right. So there was something that we observed actually. That was that every advance in terms of density modeling performance in normalizing flows usually seem to reduce the classification accuracy. So if you actually take an iResNet architecture style and do classification on CIFAR 10, then it gets around 8%. If you use a GLOW just with the additive blocks, so it's basically volume conserving, and you do classification on CIFAR 10, then you get around 12% error. And then if you add these affine coupling blocks, like the error increases further, And you see in other data sets that's actually even more extreme. So basically all these extra tricks, like the 1x1 convolutions, the fine coupling layers, and so on, reduce the classification accuracy if you do supervised learning more and more. So and then with the invertible ResNets, we found that that's not the case anymore. And now you have a good trade-off between, like, you have a flow model, and at the same time you have a good discriminative performance. However, there's still something to do to turn the ResNet into a normalizing flow. So we still need to estimate the log determinant of the Jacobian of the ResNet block. And in this case here, we actually have a completely unstructured Jacobian. So we don't have a triangular Jacobian anymore, so we cannot just compute it like in real NDP and GLOW and so on. But we need to compute the change of variable formula to actually do maximum likelihood-based density modeling. Okay, so it turns out that the Lipschitz constraint of perturbations of identity yields positive determinants. So that means that the log absolute determinant of the Jacobian is the same as the log determinant of the Jacobian in this particular residual network, in the invertible one. The Jacobian is non-singular, and therefore we can actually rewrite log det of the Jacobian as the trace of the log. And as f of x equals I plus j of x, the trace of the matrix log can be estimated efficiently with a power series, essentially. So we essentially estimate, our final estimator becomes this here. So it's an infinite series of -1 to the power of k plus 1 of the trace of the Jacobian to the power of k divided by k, which converges if the Lipschitz constant of our residual connection is smaller than 1, which we made sure it is for the sake of invertibility anyways. Right, so and then in practice, because that's an infinite series, we actually have to truncate it at a finite, basically at a finite number of terms, and that gives us a bias estimate of the log determinant of the Jacobian. So the final estimator is basically a truncated series, which you can see on the top, and we use the Skilling-Hutchinson trace estimator to compute this trace of the Jacobian powers. Unfortunately, this estimator is biased, and the bias depends on the dimensionality of the input and the Lipschitz constant of the network. So to train this successfully, we actually need to carefully trade off expressiveness and bias of the network. So then there's a solution, which is a follow-up work, which actually introduces uses the well-known Russian roulette estimator, which actually allows to estimate an unbiased, or give an unbiased estimate of an infinite series with probability 1 in finite time, which is exactly what you see here. And that basically means that you sample the number of terms you're going to evaluate and upweigh the previous terms by appropriate probability of this. So and then the intuition is that you flip a coin if following series terms will be evaluated and appropriately weighed previous terms. So now we have an efficient unbiased estimator that can be evaluated in finite time and can train standard ResNets as normalizing flows, basically. So here, just to show you again that this bias is actually really a problem. So if you make the invertible ResNet really expressive, then actually you end up optimizing the bias of this bias estimator. So on the y-axis, we see the bits per dimension on CIFAR 10 and then the number of epochs, and you see that the training estimate is converging and converging and converging, whereas the actual test value is basically spiking at some point and becoming worse and worse. So you really only optimize along the bias of the estimator. So then the residual flow, which is basically the version of the iResNet with an unbiased estimator, doesn't have that problem, and you stably just train to conversions. Right. So here's some examples also. So on the top left, you can now use standard ResNets with this spectral normalization to do density modeling, like just in a GLOW, and generate high resolution celebrity faces and all the other data like CIFAR 10 and so on and so on. And it turns out that these models also are on par with the state of the art in terms of bits per dimension or negative log likelihood, so they're actually very good density models, while being only based on standard ResNets. So and this method could be the method of choice for all applications where actually competitive density estimation performance and strong discriminative downstream performance is important, because now you're really just using a standard ResNet, which works well in discriminative downstream tasks. Right. Any questions up to here? Yep.
Can you please elaborate how you are making the Lipschitz constant of the function lower than the
Right. So when you do spectral normalization, you compute the largest singular value of your linear layer, right? And then you divide by that. So then you basically have the largest singular value at exactly 1 if your estimate was correct. So then we really just scale it by a constant smaller than 1. So it's like C times weights divided by the largest singular value. So relatively straightforward. And for nonlinearities, you can also use any standard nonlinearity that is used in normal deep networks because they're all basically Lipschitz usually. Yeah. Mm-hmm. Yes? Right, so that's a vague notion. One way to define it is basically the Lipschitz constant of your residual block. Because if the Lipschitz constant is essentially 0, then you have x plus something with a Lipschitz constant of 0, which is identity. So then you haven't changed anything really. So here it's really just like how much can I pull things apart essentially. But there are many other things of. Yeah. No. Okay. Anything? Yep.
Can you make any comments on how these more modern models have been playing in terms of the distortion rate theory for compressing inputs and trying to represent them more efficiently?
The flow models, you mean? I'm not sure. So I mean, so what you know is that all the information about your input is preserved, essentially, right? But I'm not quite sure how you would quantify the compression here. Yeah, in some way, when you measure bits per dimensions, then you're measuring the lossless compression of your density model. But yeah, sorry, I have no clear answer to that. Mm-hmm. Okay. Okay, so a quick summary for likelihood-based density modeling. So I talked about 3 common approaches. So one is the variation autoencoder. So we optimize a tractable lower bound on the data log likelihood of this form. We talked about autoregressive models, which apply the chain rule of probability and break up n-dimensional modeling problem into n one-dimensional conditional density problems. And then we had normalizing flows, which are concerned with designing models with tractable Jacobian determinants that are invertible and match transformed data to simple base distribution with change of variable formula. So here are some pros and cons of these different models. So variation autoencoder clearly has a big pro, which is that it's very flexible. So it has few constraints on the encoder and the decoder and the prior. However, a contra is that you can observe something which is called posterior collapse. So actually, when you actually manage your Z representation to fully match the prior, then it essentially doesn't capture any information about your input anymore. And if you have a very powerful decoder, then essentially you can learn almost useless, completely useless latent representations while your objective actually looks great. So that's a common problem in variation autoencoders. And yeah, they also have often lower negative log likelihood and worse samples than the other exact likelihood methods. But that's maybe just a matter of people sitting down and scaling them up. Autoregressive models have the pro that they are simple yet very powerful. They have very good performance in negative log likelihoods and essentially are applicable to any data modality. One contra is that the models are very different from the discriminant models we use, and sampling is usually very slow. Normalizing flows have a simple objective, and even state-of-the-art resonance can be turned into flows with one additional sort of constraint. And these models have excellent performance on joint discriminative and generative tasks. So the contra here is clearly that you need to design invertible networks with tractable Jacobian determinants, which is hard to do if you want it to be very expressive. Right. So then there are some open issues with likelihood-based models. For instance, there was a paper presented at this ICLEAR, I think, where they observed that basically if we train our likelihood-based models on fashion MNIST, for instance, and then we test it on MNIST, then actually the likelihoods assigned to the test set are actually higher than the ones are higher than the likelihoods that are actually assigned to the original test set. So the same as they showed this also for CIFAR 10, You train on CIFAR 10 images, and then you see that's basically the blue curve here is the sort of the histogram of the likelihoods of your CIFAR 10 training images. The gray ones are the likelihoods of your CIFAR 10 test images. And then SVHN, which is a completely different data set, actually gets assigned higher likelihoods than CIFAR 10 again. So if you want to use these models for outlier detection, basically here you see why that's hard. So this has to be solved somehow, and there's also a lot of follow-up work on this that tries to solve it. But that's a big problem with these models if you want to use them for things like outlier detection and so on. I said that there were some results where VAES are actually the state-of-the-art in adversarial robustness on MNIST. However, if you go to more complicated data sets, like CIFAR 10 and so on, then that breaks completely down, and they're not robust at all anymore, these class conditional generative models. And here you can also see something else, where basically when we train a class conditional generative flow and we condition on the wrong class, and basically here you see two histograms. So first of all, the blue on the left is the negative log likelihoods binned that you would get from conditioning on the second, so basically on the top wrong class, and then the red ones are the negative log likelihoods you get by conditioning on the correct class. So you have a conditional generative model and condition on the wrong class and the correct class and bin these, and you see that basically the change in likelihood is smaller than the variance over the data set. So you cannot really expect these models to be reliable in detecting adversarial examples, for instance. Right. And strong models on both classification and log likelihood metrics are still an open problem to some extent, because this is clearly a phenomenon that is not desirable. Okay, so to summarize, overall the pros of likelihood-based generative models are that you have a principled and powerful objective to train and quantify progress. Likelihood allows you to measure generalization on the test set, so memorization of your training set is not enough to do well here. Normalized densities can be used for downstream tasks like outlier detection, or you can do robust classification with class conditional generative models, etc. However, in challenging scenarios, these are still pretty much like ongoing research problems. But potentially, these models will be very useful in these domains. So there's still much work to be done. Okay, so thank you very much. And so now we have some time for questions, I think. Yeah.
How do these models compare to, for example, GANs in terms of required training data?
Sorry?
Required training data, the amount of training data.
So it's hard to benchmark generalization of GANs, right? So it's not clear how to compare these types of models in a rigorous way. So there's not really any answer to that. And that's what's nice about likelihood-based generative models, that actually there is a way to check for generalization.
How about the diversity of samples?
They're pretty diverse, but often too diverse, actually. Because if you fit a flow, for instance, with the forward KL divergence, what you end up with is a model that actually has higher entropy than the data itself. So you actually see, like, people use all kinds of tricks of temperature scaling to sort of reduce the entropy of the model they sample from. So yeah, pretty high diversity, and even too much sometimes. Yeah. Yep. Right. Well, so essentially so you have the two terms in your VAE objective, right? So the first one is really just about the reconstruction from your latent code, and then the second one is the KL divergence between your Q of Z given X and your, oh yeah, I can go back to that actually. Oh yeah, here we are. So your Q of Z given X and your P of Z. So and once you actually fully match your prior, then there's essentially no information in your latent code anymore. So and then you can, maybe you still encode your images into a couple of dimensions, so you can still decode them with a powerful decoder, but you haven't learned any useful latent representation. And that's a problem that's really not clear how to fix. Yeah. Yeah, so people have worked on basically using flows to get more flexible posteriors, and yeah, that doesn't solve it really. I mean, yeah. So I think it's pretty much an open research question with like a lot of papers written on it. Yep. Is there other metrics other than also likelihood for general Right. Yeah, there are other metrics like other divergences and so on, but those are usually hard to estimate. So for tractably training models, there's really just the forward KL as far as I know. I mean, yeah, you could, yeah. If you train an autoencoder with a mean squared error loss, for instance, then, yeah. Yep.
What's your opinion on methods like Wasserstein autoencoders that approach?
Oh, yes, the Wasserstein distance, of course. Yeah, we have, okay. The Wasserstein autoencoders, I'm not too familiar with them. Right. Yeah. So I cannot really tell you too much. But yeah, there's basically, if you have one Lipschitz discriminators in your GAN, then actually you can show that this is basically a lower bound on the Wasserstein distance. So there's that's another way of actually having a principled way of evaluating your model. So that's another option. But it's hard to get one Lipschitz discriminators to work. Mm-hmm. Yep. Mm-hmm. Sorry? No. So basically, what you get is when you spectrally normalize your weights. So you basically bound the largest single value. That again bounds the spectral radius, and then that's basically enough to show that the fixed point iteration would converge. Mm-hmm. Sorry, I don't understand. You don't have what? In the unsupervised setting? Well, no, that's, I mean, did I say, I didn't. I mean, you have, I guess you can easily, I think there's papers that show that in the unsupervised setting you can also essentially generate adversarial examples. So basically data points that are nothing like your data but still get assigned a very high likelihood. Yeah. Yeah.
Will there be a theoretical lower bound of the negative low likelihood of those predictive models?
I'm not sure. Sorry.
Any last questions? No? All right. Thanks, Jörn.
Thank you.